In this work, we propose analytic conditions for differentiable collision detection and trajectory optimization. The goal more broadly is to enforce non-penetration of convex sets while optimizing over their configurations. This is important in collision-free trajectory optimization, where these convex sets can represent collision bodies, and we want to find trajectories where these bodies do not collide. Traditionally, this is done with a bi-level strategy, where a trajectory optimization solver explicitly calculates the separation distance between bodies at each iteration. A lower level problem must be solved multiple times in order to enforce constraints on the separation distance. In contrast, we present a set of smooth, analytic, easy-to-compute conditions which can enforce non-penetration when embedded as constraints in a single-level problem. Due to this approach, our method is able to reliably converge to an accurate solution for the distance between bodies over time. Single-level methods similar to this exist, but they require the enforcement of non-smooth complementary slackness conditions, which we are able to forego. For the purposes of trajectory optimization, we consider the distance between bodies to be the minimum offset to touch. This is the minimum offset that either set must undergo without rotation in order to intersect the other set at its boundary. We derive the following conditions that are only met at a minimum offset to touch solution. One key insight is that at the solution, the surface normals point in the direction of offset. Note the lack of complementarity constraints, which make similar approaches infeasible. These minimum offset to touch conditions, however, are only enforceable when we have smooth collision bodies. So, we introduce a method to create smooth, semi-algebraic approximations of polytopes. Just as a polytope is the intersection between a hyperplane and the non-positive cone, we represent our semi-algebraic approximations as the intersection between the same hyperplane and a smooth approximation of the non-positive cone. We show that our single-level, smooth optimization problem solves faster than the method presented in DCOL, which requires the explicit calculation of separation distance at each solver iteration. In this work, we presented conditions that allow a trajectory optimization solver to converge to an accurate guess for the separation distance between convex sets, and we were able to use these conditions to enforce non-penetration of bodies. While useful for collision avoidance, our method may also be more broadly applicable in the future. This approach is directly applicable when performing contact-implicit trajectory optimization, where contacts between bodies must be estimated and simulated. In addition, our method may also be used for broadly enforcing non-membership in polytopes while optimizing over their configurations. Thank you.